Conceptually, memory on a computer can be thought of as a large number of tiny boxes arranged in a line, with each box holding some fundamental unit of data, like a byte. The boxes are all labeled with a sequential number called an address, and the interface the computer provides you for working with this memory is extremely simple. As long as you know the address of the box you're looking for, the computer can perform two operations: writing data to an address and reading data from an address. And if that sounds suspiciously familiar to you, it's because in programming, what I'm describing is called an array. And in software terms, that's all memory really is. So despite the fact that they're usually very large and displayed in hexadecimal, a memory address is just another way of describing an index into the array that is your memory. In the end, absolutely everything that runs on a computer is built on top of this array. And as a result, is built using the only functionality that an array provides, which is writing data to a particular index or reading data from a particular index. Now, that can be a lot to wrap your head around if you've never really thought about things this way before. So let's just start by building the simplest possible implementation of this concept of memory, which would be an array with just one element in it, say a single byte. If we want to use our 1 byte of memory to store 1 byte of data, for example, a single English character, we don't have any choice at all about how to do it. It just goes in the one box we have at index 0 and that's it. But as soon as we have 2 elements to work with, now we have a choice. If we want to store 2 characters, there are now 2 different possible orders to store them in. 3 bytes gives us 6 possible choices, and of course, with any simple pattern like this, there's a mathematical formula to describe how many possible arrangements there are given an array of certain length, which you might remember from school as a factorial. As a result, as the number of elements increases, the number of possible choices we have for the ordering of these elements increases astronomically. And that gives us some insight into an interesting problem. If I told you that I'd filled 1,000,000 boxes with 1,000,000 random English characters, and I offered you an amazing prize if you could tell me if the letter Z was anywhere in this 1,000,000 character set, how would you go about doing it? Well, given that all we have to work with is our 2 operations of writing data to an index and reading data from an index, I think you'd quite quickly come to the conclusion that the only option we really have is starting at address 0 and checking every single letter in order until you either find a Z or reach the end of the array. In the case that there's no Z at all, it would be incredibly time-consuming. Now imagine I asked you the same question, but I told you up front that the characters in the array were sorted in ascending alphabetical order. Figuring out if there's a Z in the array is now trivial. All you have to do is look up the very last element by its index. If the final character is a Z, the answer to the question is yes, otherwise it's no. But now imagine I ask you to tell me the most frequent character. That is, the character that appears the most number of times. Chances are you'll end up resorting to just searching through the entire array again. If you try really hard, you might come up with a solution that gives you a little bit of an edge on the naive approach of iterating through every item one by one, but nothing compared to that lightning-fast, just check the very last item in the array approach that we had for finding the Z. And of our 1,000,000 factorial possible arrangements of the data, of course there's an arrangement that makes finding the most frequent character much faster, which, funnily enough, is arranging characters in order of their frequency, putting the most frequent one at the start. There are 2 foundational computer science concepts here that I think are very important to understand. The first is that because everything is built on an array of memory, and all you can do with an array is read from and write to an index, eventually every data access strategy in programming boils down to figuring out an array index. The second is that when it comes to figuring out that particular array index, every different possible ordering of the elements in that array has different strengths and weaknesses that can be exploited. And so to finally connect with this video's title, I'm going to offer you a very simple definition. A data structure is just a strategy for finding something in an array. That's all it is. Like the 2 concepts, all data structures have 2 halves. The first is the particular ordering of the elements in the underlying array. The second half is the logic used to perform operations like finding a particular element, inserting a new element, or removing an element. Our initial example showcased one of the most common and most useful data structures, which is a sorted array. Our character lookup example was extremely simple, and we were able to sort our array based on the element data itself, the character. But in a real scenario, you might be storing larger composite objects like a user, for example, and sorting those larger elements based on some subfield like the user's ID. It's also common to have arrays that aren't sorted by the data stored in the array at all. For example, if you need to look up your users by ID and also by name, you might create two arrays of indexes into your actual user array, where the indexes in one array are sorted by the user's name, and the indexes in the other are sorted by the user's ID. And notice that this data structure is actually using multiple arrays underneath. One to store the actual user objects, which may or may not be sorted, and one to store sorted indexes, which are functionally just pointers to the user objects. If you're not used to working with pointers, this might seem a little bit confusing, but you can imagine it just like books in a library. Each physical book itself can only be in one place at a time, obviously, but of course people want to find books by title or by author or by genre. So rather than duplicating the entire physical library and having 3 buildings with the same books in them, one sorted by title, one sorted by author, and one sorted by genre, the library will have a computer system that allows you to look up a book by whatever criteria you want. The book itself isn't stored in the computer, it's stored in a stable location on a shelf, and the various searches you can perform will return directions that tell you where to find that book, just like a pointer tells you where to find the actual data you're looking for. I have other videos on specific data structures that go into a lot more depth, and so in this video I'm just going to give you an overview of a few of the most common and useful data structures, and specifically how they're all implemented underneath using arrays. An array list is an ordered collection of elements, and on the surface looks very similar to an array. It supports reading and writing to an arbitrary index, but adds a few very useful features on top. The first is the ability to add a new element to the end of the list, increasing the element count of the list by 1, which is different to arrays, which have a fixed length. But if arrays have a fixed length, how can a list increase its number of elements if it's built over the top of an array? Well, in order to be able to add a new element to the end of our list, the array underneath our list actually has to be larger than the list itself. The length of the backing array is usually referred to as the capacity, and the number of items in a list is actually a separate piece of data, often called the size or the count. So when we call our ArrayList's add function, really what we're doing is we're using the list's internal count as an index for what boils down to a standard array write, then increasing the count by 1. The second useful feature a list provides is the ability to remove an element from some arbitrary position in the list, which shifts any subsequent elements backwards by 1 to fill the hole. This is much closer to how humans conceptualize a list of items, but it's not how arrays work. Because arrays have a fixed length, there's no way to individually remove one of the elements from the array because, of course, underneath that would correspond to removing the piece of physical memory that the index actually maps to. So the best you can really do with a normal array is set the data at that index to 0. In order to provide the remove functionality that a list offers using array primitives, internally, when we remove an element, our list has to copy every single subsequent element in an array backwards by 1 to fill the hole, which of course for very large arrays is extremely slow. The mirror image of the remove functionality provided by the list is insert, which can create a new element partway through a list, shifting all subsequent elements forwards, and of course also results in a copy, that is, a read and then a write, of all of those elements. This is such a good example of why understanding that everything is implemented over the top of an array is so important. As a new programmer, it's very easy to assume that if your programming language provides you with a construct like a list, common operations like inserting and removing elements should have high performance, because assumedly the designers of the language are very smart and qualified. But it doesn't matter how smart you are if you're trying to fight the laws of physics. Every ordering of elements in an array has strengths and weaknesses, and if you're leaning on the weaknesses, the language designers can't help you. But as with everything in programming, the best choice depends on the actual data that you have and the patterns of access that you're expecting. Stacks and queues are data structures that can offer fantastic lookup, iteration, insertion, and deletion performance with one major caveat, which is that you only ever insert or delete elements at the beginning or the end. A stack data structure specifically limits any changes to the last element. And the reason it's called a stack is because conceptually it's like a vertical stack of objects in the real world. If you have a vertical stack of blocks, you need to remove all the blocks on top before you can get to a block halfway down. The only block in the stack that is directly accessible is the one on the very top. A stack is functionally just a more constrained version of an array list and can be implemented in exactly the same way. You have an underlying array with some fixed capacity and an internal variable that tracks the count of how many elements there are in the stack. When using a stack, we refer to the last element in the internal list as the top. You can imagine a stack of blocks being represented on its side as array elements here. Adding an element works in exactly the same way as adding an element to a list. We just write the data one past the current last element and increase the count by 1. Stacks also provide the ability to remove elements from the list, but just like our stack of blocks, they only support removing the very last element. And if you think about it, removing the last element is actually a special case because by definition there are no elements after the last element that need to be copied to retain our ordering. So we can just reduce the count by 1 and we're done. And in stack terminology, this is referred to as popping the element off the top of the stack. And it's just worth mentioning here that there's a symmetry in these fast list operations. Really add is just a special case of insert at the end, and pop for stacks is just a special case of removing an element at the end. Because there's no elements after the end of a list, there's no need to copy any subsequent elements to create space or fill a hole. As long as our data access pattern matches the natural characteristics of a stack, that is, we only ever add and remove elements from the end, stacks provide amazing performance and simplicity. And a great use case that's often used as an example for stacks is keeping track of undoable changes in a text editor. If we push all the user's changes into a stack data structure, when they press undo, they expect only the most recent change to be reverted, which maps to removing and handling only the last element in the underlying array of changes. If you're wondering about handling redo, it's as simple as keeping a second stack of redoable changes. If the user types a brand new change in, we just empty the redo stack. A queue we can see as an extension of a stack and provides a single piece of additional functionality, which is being able to also remove elements from the front of a queue, not just the back like a stack. Queues, just like queues in real life, are used for processing things in the order that they're added, with an example being a web server processing incoming requests. If we used a stack to process incoming web requests, every new request that came in while we were busy would push the old requests deeper down. And depending on how heavy the load is on the server, the request at the very bottom of the stack might never get processed at all. Whereas using a queue would mean that responses go out in the same order that requests came in, giving us a much more reasonable median response time. So how do we implement a queue over the top of an array? Deleting elements at the end was quite straightforward, but if we want to delete an element from the beginning of the queue, surely that means we're going to have to copy all the elements backwards by 1 to fill the hole, right? There's a couple of really cool tricks here we can use. Firstly, we just need one more variable in addition to our count that tracks the index of the first item in the queue. I've also just renamed the count in this case to endIndex to make it clear what's about to happen. Now obviously the start index starts off as 0, so when we need to remove the first item, what do? Well, removing the item at the front of the queue is referred to as a dequeue operation, and all we do is just increase the start index by 1 and treat the array as if it starts from index 1. Index 0 doesn't exist at all anymore. It's a beautifully simple solution. But you can probably see that as we process more and more items through our queue, the start index will keep growing and we'll have more and more dead space at the beginning of our array, and eventually we'll just overflow the capacity of our underlying array altogether. So how do we fix this problem? Well, we can use the amazingly useful modulo operator. I'll link you a comprehensive explanation of how mod works, but in the case of our queue, how we actually use it is that whenever we want to access an element in our underlying array, Instead of directly using the index, we mod the index by the capacity of the array first. It might not be immediately obvious what this does, but you can basically think of the mod operator as generating a repeating series of numbers across a range, where each of the series has the number of elements that you mod by. Watch what happens when the end of the queue moves past the end of our underlying array. As the end index gets to the point where it would overflow, when we insert a new element at the back of the queue, the mod operator causes that index to wrap around to 0. As we continue to add items to the back and remove items from the front of the queue, the mod operation causes the entire queue to wrap around the corner like a game of Snake, allowing us to manage our queue inside a fixed size array without having to reallocate or resize or copy anything. I just found this so cool the first time someone taught it to me. This is technically referred to as a circular queue rather than just a queue, but if I ever need a queue, I always end up implementing them like this. Before we move on to a couple of the more advanced data structures, we need to learn about one of the fundamental building blocks that they rely on, which is the rather infamous linked list. Rather than leaning on the natural ordering of the underlying array to keep elements in order, a linked list, as the name suggests, keeps elements in order by linking them together. That might sound like magic, but just like everything else, it's built over the top of an array. If we were storing user objects in a linked list, a simple implementation would be wrapping each of those user objects in a struct or similar that, as well as the user, also includes the array index of the following user in the linked list. So if I start with my linked list and my underlying array empty, the first user I add just goes into index 0 in the array. Then let's say we want to add another user, which I'll call user 3. Don't worry, it's for a good reason. In addition to adding user 3 to the underlying array, I set the next index field of user 1 to the index of user 3, essentially linking user 1 to user 3. This might seem pointlessly complicated until I try to insert a user in between user 1 and user 3. For an array list, that would mean that I would have to copy any elements after the target user forwards by 1 to make space. But in a linked list, I just add user 2 to the end of the underlying array and update the next index fields so they correctly point from user 1 to user 2 to user 3. Removing user 3 would be even more simple. We just change the next index of user 2 to -1 to indicate that it's at the end of the list. So given that we don't have to do any of the expensive copying when we insert or remove an element in a linked list, if we scale this up to 1,000,000 elements, we should get great insert and deletion performance now, right? Well, not exactly. You might have noticed that when we inserted user 2, it ended up in the third slot in the underlying array, even though in our linked list it's correctly second. Because linked lists don't rely on the natural ordering of the array they're built on top of, it also means we lose the ability to easily access elements based on their index, because the underlying array index is not necessarily the same as their position in the linked list. As a result, if you have a linked list with 1,000,000 items and you want to remove something at position 300,000, in a naive implementation you would have to start at the first element and follow the next index 300,000 times before you arrived at the element you're looking for. So the trade-off we've made here is that we have great performance inserting and removing elements if we have a direct reference to the element before or after the target, but we've lost the ability to efficiently find the element at the nth position. And in addition to this, just iterating through elements of a linked list in order is significantly slower than iterating through an array, due to the somewhat random pattern of memory access having poor cache performance. Because of these particular quirks, I find it quite rare to actually use a linked list to store a normal collection of ordered elements. But because of some properties that they have, they make fantastic building blocks to put other data structures on top of, just like linked lists themselves are built on top of arrays. Just a small note before we move on. If you've done some programming before, you might be a bit confused thinking, well, the linked lists that I implement don't use an array. I just create the nodes using the new operator or malloc, and they don't use indexes for the links, they use pointers or references to each other. And that's a totally valid point of confusion. It's something I didn't understand properly for a long time either. But given that the way that software interacts with memory at the lowest level is an array, pointers are really just an index into memory. When you use the new keyword or malloc or similar, What you're doing is you're interacting with an internal data structure, which is usually referred to as the heap, provided to you by the programming language or the standard library. And of course, what that data structure is built on top of is an array of memory provided by the OS. And in practice, the data structure for heap allocation has to be extremely generic in order to handle any possible workload. And as a result, if you allocate your linked list nodes using new or similar, you're likely to get worse performance than if you were managing it inside an array yourself and using indexes. Now, I know I promised you some more advanced data structures, so let's crack on. Next up, we have the Hashmap. Hashmaps are also sometimes referred to as dictionaries, and they're incredibly common and useful data structures. Instead of using a numerical index to look up data, a hashmap uses some other kind of data like a string, which we call the key. In this case, we're looking up the prices of flowers using their name as the string key. And of course, because you know that a hashmap has to be built using an array, you can probably guess that there must be some way of transforming arbitrary data like a string into an array index. And indeed there is. It's called a hash function, and it's where hashmaps get their name. Calling a hash function with a string key will give you back a number that's reasonably evenly spread across a large range, like the maximum of a 32 or 64-bit integer, and because that number is too large to feasibly use as our array index directly, we can use the same modulo approach that we used for our circular queue, and just mod the array index by the length of our internal array. This maps the output of our hash function into a repeating range of 0 to the length of the array minus 1, which means we've converted a string into a valid index in our internal backing array, which solves our original requirements that we had. But what happens if our approach returns us the same index for two different strings? That's called a collision, and there's a couple of ways to handle it. The first approach remains resolutely committed to using a single array to store the data. If there's a collision, we just iterate forwards through the array until we find an empty slot, and then read or write the data there. Of course, this means that after we've converted our string into an index, we can't just assume that the resulting array holds the data that we want. We need to store some identifying info like the flower name in each hashmap item so that we can compare to see if it's actually the item we want, and if not, start iterating through the array and comparing until we find the data that we're looking for, or an empty slot indicating that the key we're looking for doesn't exist in the array at all. This approach has some downsides, with the main one being that it trends towards creating long consecutive runs of stored elements called clusters, which means that you might need to iterate for a long time until you find an empty slot. An alternative approach of using just one array to store your hashmap is using two arrays. And the great thing about this is it'll allow me to demonstrate one of the really cool characteristics of a linked list that's not very well known. So in this approach, instead of storing all the items in one array directly with all the collisions stored consecutively, we use two arrays. We store the first item for a particular hash in the first array, and to handle any collisions, we give each item an index of the next collision, forming a linked list. All the colliding elements are then stored in the second array and linked together. Looking up items with this approach is very similar to the one array approach, except now we're following a linked list instead of iterating forwards through an array. And you may or may not have noticed, but the cool linked list trick I mentioned earlier is already visible. One of the most amazing natural properties of linked lists is that because the underlying array items don't need to be consecutive, it means that we can store multiple separate linked lists of the same type in the same array. Each of our hashmap collisions results in a new linked list being created, and it doesn't matter at all that all those lists are interleaved in this second array, because we're following links, not iterating through array indexes. If you wanted to store collisions in ArrayLists instead of linked lists, you would need to allocate a separate ArrayList for every collision bucket, which would end up being a tremendous number of allocations, and even then you can't really predict ahead of time how the collisions are going to be spread across buckets, which further complicates capacity planning. You'd probably need to make those arrays resizable. So that's an awesome natural property of a linked list. You can store multiple linked lists of the same type in a single array, even if you don't know ahead of time how the total capacity is going to be spread out between those linked lists. In all the data structures we've discussed so far, the only relationship between elements has been the order in which they appear in the array. A link between two elements in a linked list doesn't imply that there's any particular relationship between those two elements, just that one appears after the other. But there are some cases in which tracking relationships between elements is incredibly useful. If you're building a user interface, you intuitively understand that there's a relationship between the elements in the interface. Rather than every element being positioned relative to the screen, UI elements can be positioned relative to each other, to their container or parent element, so that when the parent moves, all the children implicitly move too, in a single update, instead of having to set the position of every internal element manually. This type of structure, when visualized, looks like this. And the name we generally give to this type of data structure is a tree. Each of the elements in a tree is called a node, and the relationships between nodes only go in one direction, from top to bottom. We refer to the node at the top of a relationship as the parent, and the node at the bottom as a child. Each child has only one parent, but each parent can have multiple children. So how is a tree built over the top of an array? In much the same way as our Hashmap implementation, we can easily build a tree over just two arrays by using linked lists. If you think about it, a tree is actually very similar to a linked list, except instead of each element pointing to just a single next linked element, in a tree, each node can point to multiple different nodes after it, which we call the children. And if we can build something using a linked list, that means we can build it using an array. We can start to implement our tree by placing all the nodes of our tree into the first array. Each node has a child index which points into our second array, which stores the relationships between the nodes. Each relationship is just a simple object containing the index of the child node in the first array and the index of the next linked list item in the second array. That is, the next child. So if we wanted to traverse downwards through our tree to the icon of the first menu item in the list, that little new document icon, what we're going to do is get the first child of the dropdown, which is the menu item, and then the second child of that, which is the icon. So in terms of our underlying tree operations, we would start at the root and follow the child index into the second array. Because this is the first child, we'll follow the node index back to the first array, and we've got our first menu item. We then follow the child index to the first child of our menu item, which is the new text, and instead of going to the node, we follow the next child index to get to the second child of the menu item, which is the icon, and then follow the node index back up into the first array. This is just one of many different ways you can implement a tree using arrays. There are approaches that can pack the tree into a single array, and there are approaches that will give you better performance with larger trees if you know the details of the data you're planning to store and the way you're planning to access it. And now a tree data structure in academic terms is actually a constrained version of a more generic data structure called a graph. If we take a look at our tree, remember how I mentioned one of the constraints of a tree is that the relationships are asymmetrical? A parent can have multiple children, but a child can only have one parent. Well, if we relax that constraint and allow a child to have multiple parents, we now have what's called a graph. The easiest way to think of a graph is in terms of starting with our linked list and progressively removing the constraints. A linked list only allows us to have a single link from the previous element and to the next element. A tree relaxes that constraint by allowing us to have multiple links to next elements, creating the parent and children relationship. And a graph takes it further by allowing us to have multiple links from previous elements as well. And in graph terminology specifically, those links are referred to as edges. The nodes are sometimes referred to as vertices or vertexes, but that's a little bit less common. I tend to just call them nodes. Likely the most well-known use of graphs these days is something called A*, which is a pathfinding algorithm. That is, it finds the shortest path between 2 points, and it's used in an enormous number of video games for calculating the best route for a character to travel from their current location to a target location. Graphs have been a topic of very focused academic research for a long time, and I'm not going to go into too much detail here, but in the spirit of the video, let's have a look at how graphs are implemented using arrays. Well, as it turns out, I don't even need to because the implementation is exactly the same as the one I gave you for the tree. You store the nodes in your first array, and the edges in your second array, and each node just stores the index of the first edge in a linked list of edges. The difference in this case is in the operations, not in the data arrangement. There are some specialized types of graphs that require a slightly different implementation, But in the vast majority of cases, you can get away with just 2 arrays underneath. The one notable difference is that if you want to traverse in any direction through the graph rather than just from parent to child like you do in a tree, you'll need to store a duplicate of the vertex so it's accessible in both directions from both nodes. I hope this has given you a nice overview and helped you build some base intuition for what a data structure actually is. And if a lot of this felt very new to you, I have one final piece of advice, which is to start simple. The next time you're approaching a novel programming problem, try building it using just an array. See how far you can push it. You really will be surprised at how much you can achieve with just a single array. And who knows, by doing that, you might come up with a novel data structure that fits your data and your situation perfectly. Enjoy!